To today's Gemini Center Quantum Communication and Security Track meeting, where we have the pleasure of having Alexander Mueller-Hermes to talk to us about his ongoing research in quantum information theory and the study of quantum protocols. Please go ahead when you're ready, Alexander.
Can you see the slides? So,
I see the slides, yes.
okay. So maybe like this. Can you see it?
Yeah,
Or
perfect.
okay. Yeah, so this is, yeah. You say ongoing work, right? So what I will talk today is mainly old work. So, but it's still ongoing in the sense, yeah. There are still open questions and we are still working on it. But so what I will talk today is mainly contained in this archive preprint. It's been published in IEEE Transactions on Information Theory. So this joint work with Matthias Christandl, who's at QMath at University of Copenhagen, and I'm actually there right now. So yeah, so that's where lots of this happens. So okay, so this is about fault-tolerant coding for quantum communication. And so let me start maybe with this question: why do we need quantum communication? And we were already talking about it. So there's like the two basic scenarios that you might have in mind. So one is maybe the quantum networks, where you have distant cities or quantum computers in distant cities that you want to connect and where you want to establish entanglement between these locations. We've already been discussing that there's maybe not, not so many use cases for this. Maybe there's some like nice scientific use cases for this. Anyway, another interesting application that I think has much more use cases is like on-chip communication. So where you can like envision like a quantum computer built up from several cores, so quantum cores that have to send quantum information between these cores. And for example, like if you know ion traps, then there's like this fundamental problem that you cannot put in, an arbitrary number of ions into the same trap. So what people are proposing there is to have several traps of ions that they then connect and build up this shared entanglement that they then for building computers. So this is, I think it's a very nice application area for quantum communication.
Can I just
Okay,
comment?
yeah,
This seems to be exactly what IBM is doing with their like System 2 or System 1 or whatever they call
this
it.
is also true. It's not only trapped ions. It's many architectures. Okay, so these are maybe the two basic scenarios that one can have in mind if one wants to have like uh, an application in mind. So let me now state the setting in which we work and the main problem. So I want to consider a very simple setting where I just have two quantum computers and there's some physical communication channel that, let's say, transmits qubits. And the main question of quantum channel theory is what the maximal rates are. So by rate, I mean the number of qubits that you can send from quantum computer A to quantum computer B per channel uses. You could also look at a classical communication. Then you would consider number of bits per channel use. And you want to do this in a reliable way. So this physical communication channel will be noisy. And so you want to do this in a way where you can control the level of noise of the overall transmission. So you want to push this to zero. And what I want to consider now is a scenario where I have some kind of realistic assumptions, not only on the noise of this physical communication channel, but also on the noise affecting the quantum computers. So let me maybe talk a bit about noise. So what I mean by this is that there's usually two sources of noise in these settings. So one is, of course, the physical communication channel that is usually modeled as a noisy quantum channel, say a depolarizing channel of some strength P. But the other source of noise that you have in quantum computing is that the quantum circuits that you run have there's a certain gate error probability Q, by which your logic gates fail or don't, I mean, by which they deviate from the ideal operation. So for this, one should note that typically this gate error probability Q is much lower than the noise of this physical communication channel, right? I mean, unsurprisingly, if you have a long communication line, this will introduce much more noise than what happens on your device that you have tuned maybe very well. So the objective for us is now to send information with a final error rate as small as we want. So we want to be in this Shannon theoretic setting where we can push the final error rate as low as we want, and it should not depend on either P or Q. That it doesn't depend on P, that's somehow the quantum Shannon theory flavor, but it should also not depend on Q. Okay. So the main ingredients for this to achieve this goal somehow is quantum Shannon theory and fault tolerance through quantum error correcting code. But somehow the challenge lies in the communication of these two worlds. So let me start with outlining a bit of quantum Shannon theory, maybe mostly known to people here. So let's consider this purely quantum Shannon theoretic setting of classifying the optimal communication rates. So what you usually see is drawings like this, where you have this noisy communication channel. Think of it as a depolarizing channel, if you want a concrete example. And what the sender and the receiver can do is they can choose some encoder and some decoder. So the encoder will take a message state of say n qubits and encode it into some quantum state of m qubits that go through the channel, get distorted by this noise, and in the end, the decoding party applies this decoding channel that should give the message back, ideally the message with some error probability epsilon. And usually, one wants to have usually to consider like a uniform error here over all the possible messages, which then leads to these kind of maybe diamond norm expressions that your composition of the encoder, the channel, and the decoder should approximate an ideal qubit channel of nm qubits that you want to send. So the best error that you could hope for is a minimum where you optimize over all the encoders and the decoders. And this you could call the optimal coding error. And now in quantum Shannon theory, what we do is we take somehow the asymptotic limit of this number of channel uses going to infinity. So in this asymptotic limit, I can then compare the number of qubits that I can send, so the nm occurring in the exponent or in the tensor exponent of this identity channel here, and I compare this to the number of channel uses that I have used. And this limit is called an achievable rate if this optimal communication error goes to 0. So this is kind of the setting that we are in, and we would like to know these achievable rates that you can get. It's an insight by Shannon that is somehow surprising to people who have never thought about this, that this can actually be non-zero, right? So it's very easy to build coding schemes where you just maybe repeat the message. If you send classical information, you can just do a repetition code that somehow will have a 0 rate, but you can make this communication error go to 0. What Shannon realized is that you can actually get this asymptotically 0 communication error at finite rates. That's somehow the interesting thing. Okay, are there any questions regarding this? I don't know in the audience. I mean, this should be very well known, maybe. Okay, interrupt me if there are questions. So I also have to say I have to minimize somehow your faces, so I cannot even see whether you are unhappy about what I'm saying. So please make your voice go. Say something. Yeah. Okay. So so the quantum capacity is somehow this fundamental quantity that one might be interested in, and that's the supremum of achievable rates. So again, like achievable rates meaning the number of qubits divided by number of channel uses in the limit of infinitely many channel uses, such that the communication error goes to 0. And there's this incredibly nice formula or not incredibly nice, there's a nice formula by Lloyd, Shaw, and Devitak for this quantity. Namely that this quantity is equal to regularization of a certain entropic quantity, which is called the coherent information. There's a quantity that you can compute for a channel. And yeah, in classical channel theory, somehow this is the end of the story. But in quantum channel theory, you have to do this kind of regularization where you take this quantity, this it's a certain type of entropy, and you apply it to this to the tensor power of your channel, and you normalize by the degree of the power that you took. And then you have to take the limit of k going to infinity. That leads to this. This is precisely equal to this quantum capacity, this optimal communication rate. So somehow this, the details of this are not important. It's just to say that we somehow, there is a formula for this, right? It's not an easy formula. It's not even clear whether this is computable, but it's a formula that you can write down. So in particular, what we know is somehow, if we just take the proof of this formula, then we can get a guess of maybe how some encoder and decoder pairs could look like, this kind of particular operations that Alice and Bob could do. And somehow what they might look like is like this, that you take these n qubits here, then you put them through some isometry where you have a very large output dimension, and then you randomly choose the unitary, and with high probability, this will give a good input state for the channel. So it's somehow like the way of how you construct these coding maps in the proof of this LSD theorem. There are efficient constructions known for this encoding maps, but so far there are no specific, no efficient constructions known for the decoder. So particularly the decoding is somehow difficult for quantum, which is ongoing investigation in quantum channel theory. But let's put this under the rug. The only take home here is that these operations are pretty complicated. So it's not something that is somehow doable, if there's noise on these qubits, right? And it's a complicated operation. So there's no hope to implement these coding schemes without having some control of the gate errors that affect your quantum computer, right? So you need a quantum computer to implement complicated operations like this. And if there's gate errors, you have to somehow address these gate errors. So let's talk about fault tolerance and the threshold theorem. This is the other part of this story somehow. So in quantum computing, what you usually consider is a quantum circuit that you want to run on a noisy quantum computer. And a quantum circuit we just understand as a circuit composed of so-called elementary operations. And there are different choices for this, depending maybe also on your hardware, but we can just pick a certain set of these elementary operations for simplicity. So typical set would be like the single qubit gates, X, Y, Z, the T gate is very important, and the Hadamard gate. Then you need to have some 2-qubit gate. So the C0 gate is a popular choice, which is drawn in the circuit diagrams as these little plus connected to a dot. Of course, you have the identity gate, which is a qubit at rest, which in ideal quantum computing, it would not matter. But if you have a noisy quantum computer, then identity gates or idle qubits, this matters. And you have preparations and measurements in the computational basis. And maybe you also have the ability to do partial traces, like throw qubits away. You can forget about a qubit and just let it, get lost. So if you have these kind of elementary operations, then you can build, as in this example, you can build complicated quantum circuits out of this. And in these quantum circuits, it's important to note that there's this notion of time, right? You could always think of the operations that you do in the first time step, then the second time step, third time step, fourth time step, fifth time step, and so on, right? So I should say two things. So this set of elementary operations that I put here, this is a universal set. It's even redundant. So you could do with a smaller set, but in particular, this set is universal. And this means that if you build quantum circuits from these operations, then they are dense in the set of quantum channels. So any quantum channel that I would like to do, I can approximate using circuits of those. Maybe this approximation is not efficient, but this is not so important for us. Only important is to note that it's possible. So then the next thing I have to say is that now once we have this notion of time, I can introduce a noise model. And a popular noise model in quantum computing is this Pauli IID noise model, which basically is a noise model that after each time step, you insert a depolarizing channel with a depolarizing probability Q onto each of these lines in the quantum computer. So this somehow makes out of our circuit a quantum channel, if you want. And quantum computing, the art of dealing with noisy quantum computers is somehow to make something useful with this quantum channel that you got from introducing this depolarizing noise. Okay, so that's the basic setting in which we are. So now how can we protect quantum computations against noise? The usual way of doing this is, again, by doing quantum error correction. So what this means is that you somehow combine several physical qubits that have this kind of gate error probability Q or this error probability Q. You combine this to a logical qubit that somehow should have a lower error probability. The way you can do this is, for example, with a 7-qubit Steen code here. So this means that I take 7 qubits together and I form these kind of funny looking states. So here, for example, to make a logical 0 state, I take the superposition of all of these states, normalized accordingly. And this will be my logical 0. Then I have a logical 1 by applying X gates to this state. And these are two states that are, that I can use to represent my information. And that is protected against general 1-qubit faults. So if there's one of the qubits undergoing some noise process, I can always recover this by looking at the outcome states.
Excuse me, Alexander, can I ask a question?
Sure.
Is this 7-qubit Steen code, is it a purely quantum code, or is it also, does it have a classical version?
I mean, it's constructed from 2 classical codes. It's kind of this CSS code construction by Shor. Like it's based on I think some Hamming code, and
so it's okay.
Yeah. So usually you have I think you have a pair of a code and a dual code, and you combine this into a quantum code. That's one popular construction. Yeah.
All right. Thanks. Yeah, I'll look it up. Yeah.
Yeah. So it's not so important how you for us how to get this. It's more important that it exists. So if you have a code like this, so the 7-qubit Steen code, for example, you can build these concatenated codes for better protection. What it means is that, so in the first level, we encode a logical qubit into 7 qubits, but then we can do the same thing with the logical qubits. So we can take 7 logical qubits of this first level and make a Steen code on a even higher level. And we can build this up, on and on, right? Without end, and get better and better protection, or at least we would hope to get better and better protection. So, and this is somehow what you can do. And indeed, this is it's a very nice construction that you can do to realize fault-tolerant quantum computing. In a sense, it's I think it's more or less the only like nice construction where you can prove it, like the threshold theorem, rigorously. So this may be a strong statement, but I think it's true that there are not so many rigorous proofs of the threshold theorem for other code families. So that's by far like the best understood construction, I think. So what's the threshold theorem that I've now mentioned? It's this theorem by I should not have said, so Aliferis, Gottesman, and Preskel. They are the ones that prove this version of the threshold theorem, but this goes back to Aharonov and Ben-Or and others, Kitaev, and there are many versions of this. So what these theorems say is that there exists a threshold Q0 that is a non-zero number for this is compared to the noise of your quantum computer, such that for every circuit gamma that you have, you can encode the circuit into a certain level L of this concatenated code. So this is what I mean by gamma subscript CL. This is gamma encoded into this code, where basically I replace each of the gates in gamma by a gadget on this code and an error correction. Then I can hit it with my noise model. So this is what I mean by this the square brackets and FQ. So now I take this gamma, I implement it in the code, and now I apply this Pauli noise model. So after every time step, I put this deployment channel on all of the qubits. So that's my faulty version or my noisy version of the encoded circuit. Then this quantity is close in norm to the ideal circuit up to some error that is doubly exponentially decreasing. So the Q should be smaller than Q0. So this is, the quotient will be less than 1. You take it to the power 2 to the L here, and times some universal constant and the number of elementary gates in your circuit. So there's a lot of details, right? So in particular, what you should note is that if you have a fixed circuit gamma and you let L go to infinity, then this error goes to 0, right? So, and you can make a more refined statement about the L's that you need and the overhead that this the overhead that this fault-tolerant scheme introduces. So this is some of the threshold theorem. So it tells you that no matter what circuit you want to do, if your gate error probability is less than the threshold, you can do it at some high level of this concatenated code up to some error that you can control and get close to 0. I should also here, so this might be a bit funny looking. Circuit for me means and in fault tolerance in general usually means something that has a classical input and a classical output. So this is essentially a random variable, this gamma here. So the case of quantum input and quantum output is something more complicated. So it's really like here. No, it's not like here. Great pedagogy. So usually you have some starting point that starts with preparations and then it ends in measurements. That's what you usually think of as a quantum circuit, and then this threshold theorem works. You can modify it if you have quantum input and quantum output, but that's more complicated. Okay. So this is a threshold theorem. This is kind of clear to everyone. So I take a sip of coffee and you ask questions.
Sorry, Alexander, does one know anything about whether this Q0 is below a half, above a half, anything? I mean,
it's very much below a half. No, I think there's always like the things that you can prove about it, and I think it's probably like there's a 3-9 figure, right? That you want to go below, like the so what does this mean? So maybe 10 to the minus 3 or something is maybe a thing that you can prove. But if you do numerics, it indicates that the real threshold might be higher for many codes. So usually, like, you can also define this for surface codes and for other code families. And numerically, you find that this is somehow should be higher, but then you can only prove so much. So
right, because obviously this threshold theorem refers to all gammas of a same sort, and presumably if you as you say, you have to choose your gammas to be in the same kind of family of codes or of circuits. And then the Q0 will change with the family you choose?
I think it depends. It depends more on the code family. I mean, okay. So I suppose if you choose your gadgets badly, then it will also affect the it will affect the it doesn't matter really on the gammas. It matters on what elementary gate set you use and how you implement it on the codes. So I think in this threshold theorem by Aliferes, the value for the Q0 comes from the complexity of implementing a C0 on the code space. That's the most complicated operation. So that's some of what determines the provable Q0.
If I recall correctly, this is also the bottleneck in current implementations, right? Like there is this race happening in the industry where you're trying to essentially reach accuracy levels that are high enough that you actually go past the threshold and then you have full fault tolerance. We haven't reached it yet, I believe, but we have seen good signs that we are approaching it. But indeed, like 2-qubit gates like the CNOT are like the main bottleneck if you want to do fault tolerant circuits and not just single qubit.
There are two issues, right? So what I was referring to is the size of the gadget implementing a CNOT, right? This is like purely the number of elementary gates that you use. But of course, like for the physical CNOT, what error you get, this is usually the highest error that you have in these in quantum computers. Yeah. Okay. So if there are no more questions, then let me continue. So this is somehow the threshold thing, right? This is somehow what justifies the whole endeavor of quantum computing, if you want, right? So when Shor came up with this algorithm, people were saying that maybe there's no fixed error rate that you could realize quantum computing, but this is what the theorem proves, that you can, when you reach the threshold, then you can scale it up. Okay. So let's now summarize. So we have seen this in quantum channel theory. We have this setup where we have an encoder and a decoder at this noisy quantum channel, and we want to get a noise-free channel with a probability that gets as small as we want. The assumptions here is usually that the encoder and the decoder are perfect operations. And in fault tolerance, we have the kind of a similar thing that you can implement a circuit in an error correcting code such that the faulty version of this implementation gets close to the ideal quantum circuit, where again you can push the epsilon to a number as small as you want. And the assumption is that this circuit level noise, is below the threshold. Okay, so that's the setup. So let's put these things together. So the naive approach is I think the following. So you can choose your encoder and the decoder to be quantum circuits. They will in general not be efficient, as I said. I mean, they might have be exponentially long quantum circuits, but I mean, this is maybe less important if you focus on this on the problem of determining a rate. This noisy channel, as I said, will usually be too noisy to apply the threshold theorem. So we are interested in, if you want to build a communication line, you don't want to restrict it to the nanometer scale of your quantum computer, right? You want to make it very long. So we cannot apply the threshold theorem to the entire scheme. So what we maybe could do is we could apply the threshold theorem to the encoding circuit and the decoding circuit. So this now leads to an immediate problem, that the output of this encoded circuit, of the encoded encoder, if you want, the output is logical, right? It's in the logical space of your circuit level code. But this has to go through the quantum channel. So now you want to send somehow these systems through the quantum channel, and the quantum channel will make something physical, right? But this has to then put into the logical space of another code. So there's somehow a mismatch here. So if you use 7 to the L qubits, so maybe what you could also do is, right, you could make an entirely new code by somehow combining the quantum channel code and the concatenated code, but you would need a lot of channels to do this, right? So this number of qubits that the concatenated 7-qubit code uses is exponentially large in the level. So you would need a lot of channels to get this through. And this is unlikely to be achievable with high communication rates. So in particular, if you want to make this the overall error as small as you want, you would have to increase the level here, which then means that you also have to, again, your number of channels has to scale even more, and get a non-zero rate by this. At least when we tried it, we're not able to go this way. So this is somehow this naive approach. This somehow, yeah, it doesn't really work. These parts that somehow don't fit together.
Question.
So yeah.
Does this show up classically as well? So I know that we don't really encode data at rest, but there are like space probes and stuff, right? Where you have to use coding for data at rest.
Yeah, but yeah, usually like the noise rate of classic computers is so low that it doesn't matter.
Right.
I think it might matter in extreme situations. Like so I read this in one book that some of the areas where this matters might be a robot entering a nuclear power plant or something like this. So sure, then maybe it matters. I think it would also be an issue classically if you wanted to to have a high error rate on your classic computers. But in practice, there are a few situations maybe where this happens.
Yep.
Yeah. So okay, so this is somehow a problem, right? When we put things together. So our idea, okay, it's simple, is somehow to put in an interface. So in particular, what we want to put in is a logical to physical interface circuit. So where on one hand we have the level L of a concatenated code, and on the other hand we have a physical qubit. So this, remember that the concatenated code encodes a single qubit, so we should be able to translate this logical information to a physical qubit. So such circuits exist, and they are not too, not too difficult to build, but they of course have an obvious problem that they cannot be fault tolerant. So when you have a circuit like this, then imagine that you have this noise model where after each time step you put in a depositing noise. Then of course there's a noise event where you put the depositing channel on this last physical qubit, and that has a high probability. That has an error probability Q. So some of these noisy interfaces, when you have noise, they are only epsilon close to the ideal interface, where this epsilon cannot be made arbitrarily small anymore. So this epsilon can actually be realized to be a constant multiple of this gate error probability. So C times Q, where C is independent of the level L. And that's somehow the best that you can hope for, because as I said, your physical qubit might be hit by noise, and then the probability that this is bad is already Q. So it has to be linear in Q at best, and you can make it linear in Q. So this is somehow nice. You can make these interfaces, at least with this epsilon. So when you have this logical interface to physical interface, and same for the encoding. So you also want an interface that takes a physical qubit and produces the corresponding logical state, or attempts to do in the noisy case. Then you can consider this effective communication channel, which is the physical channel T composed with these interface circuits. And if you believe me, right, this epsilon, that this will be C times Q, then it's not too hard to believe that. So this is actually, noise model specific, of course, what this channel is, but it will somehow look like this, that you have like with 2 times C times Q, you have some channel that you maybe don't know, that's somehow the noisy version of this interface, whatever this is. But with the opposite probability, you get your channel T between the logical spaces. So this is a kind of a different channel, but then we can use a coding scheme for this effective channel instead for T. In the end, like this, so this will achieve certain rates. And if Q here is small enough, then we can relate the rates achievable for T, so for the effective channel, to the rates achievable to T by a simple continuity bound. So these capacities, they are continuous. So if you are close, if this channel is close to T, then the capacities don't differ very much. That's kind of the high level idea. So I should say this is so this is some of the complete scheme, how it looks like. So you have this physical channel, you put in the interfaces, then you build your circuits for the effective channel. use the concatenated 7-qubit Stein code here, and you put this together. And what you can show is that you will achieve rates that are somehow close to the quantum capacity of the effective channel. And as I said, the capacity is continuous, so you can relate this to the quantum capacity of T with some error function that depends on the continuity of the capacity that is explicit. It's a bit complicated, but for us it's important that it goes to 0 as Q goes to 0. So particularly if Q is small, then you can guarantee that you can get close to the quantum capacity of the channel, even in this noisy setting. Okay, so this is somehow the ideal case. Let me mention in one slide what I have put under the rug here. So because it's not as simple as this might sound. So what I put under the rug is that you have to do, of course, a proper analysis of this setup. So this kind of there's the noise model of the circuit that actually this can make these interfaces fail. And when these interfaces fail, if there's already some noise on these on the physical qubits, then they can interact with the failing interfaces. So what this can lead to are correlated correctable. So there might be correlated correctable faults on these qubits that then get correlated by this faulty interfaces. So how you can think of this is that each effective channel somehow not only connects to the logical space that these qubits have, but they also connect to the space where errors are represented, which you can think of as a kind of a syndrome space. So if you know that errors are in quantum error correction are specified by their syndromes, you can somehow get a certain mathematical or abstract description of the errors by associating to these some quantum system. And so effectively, the effective channel is actually not a normal quantum channel, but it's kind of what we call an arbitrarily varying channel. It's a particular channel that has an additional input over which some correlations can be introduced in the copies of the channel. And to deal with this situation, because arbitrarily varying channels are actually quite scary in quantum channel theory, you can use a certain post-selection trick to relate this arbitrarily varying channel to a channel of the form that I had shown before. And this is actually a normal quantum channel, where now you have a convex combination of your ideal channel T and a convex combination of the depolarizing channel. If you code for this channel, then your coding scheme will work. This is what you can show. Okay, so this is one more technical slide. So what this leads to are these kind of nice, what I think we call threshold theorems for capacity. So there exists this threshold Q0. That's basically the threshold for the circuit level for the concatenated 7-qubit Stein code, such that any rate R that is greater than this this number here is achievable using coding schemes affected by Pauli IID noise of strength Q below Q0. And what I mean by this is, again, that we can make encoders and decoders such that we can push the overall error to 0. So the overall error is not controlled by Q. It's controlled. It can be made as small as we want, as long as the rate is larger than this quantity. So note here that it's somehow strange that what enters here in terms of entropies is this kind of coherent information of the tensor power of the channel divided by k, but it's not the limit of this quantity. So remember that the limit of this quantity is the quantum capacity, but here we can only relate the rate R to this quantity without the limit. And that has to do with this issue that I pointed out, that here's actually this, that there are these correlated errors happening here, and that we have to use this post-selection trick. So
Sorry,
That's
just to because I tend sometimes to zone out. Can you remind me what K, C, and Q are?
what is, sorry?
The variables K, C, and Q, just briefly what they are again.
Yeah, so yeah, so K is a just a natural number. So you can for any K you can evaluate this function here, right? So let's fix K is to be some number, then you can compute this coherent information. C is a universal constant coming from these interface circuits. So this popped up here. That's the error of the noisy interface. And Q is the gate error probability of
Yeah,
the
great.
circuit level noise.
That makes sense. So
Yeah.
what would the K would affect sort of the size of your code or encoding?
Yes. And what I was in the middle of saying, right, is that of course you would like to take the limit of this quantity, which would be the quantum capacity. But this we cannot do for technical reasons. So we have to somehow evaluate this for any K. And then you see that there's this other term here that also this involves the square root of K. And that will decrease this. So there's kind of an interplay. So you cannot just take the limit of K here. Otherwise, this will be 0. So it's intricate. Like if you have a fixed Q, then it's not clear what the optimal K is for this formula, right? So you have to compute this. Yeah, somehow it's an annoying feature of this, and we tried very hard to get rid of this term, and we didn't manage.
So we have a question about what do you mean any rate larger than this quantity?
Yeah, so evaluate this this function. Say take K equal 1, right? Then you have the coherent information of the channel minus some term here, and take any R, then this will be achievable in this strong fault-tolerant sense.
Yeah, but achievable, you mean any rate larger than this is achievable, or what's the capacity you mean here?
No, so I mean it in this sense here. Sorry, that there exist sequences of coders and decoders, such that this rate R is the limit of number of channels divided by number of qubits transmitted divided by number of channels, such that the overall error of the scheme goes to 0.
Yeah, yes, we understand this, but the way you wrote it R larger than this, so means R can be very large
or can be 1 always.
Yeah.
Oh, this you mean?
Yeah, just from the statement. Yeah.
Should it be the other way?
Or just equal. I don't know.
No, sorry. No, there should not be any. Yeah, so
or exist something.
Yeah, I think you're right. Not any rate R is achievable, right? So I guess let me say it like this, that this rate, this function, this is achievable.
This is achievable. Okay.
Yeah. So sorry. Yeah. This is of course nonsense.
Yes. Thank you. Yeah.
Yeah. So exactly. Yeah. No, okay, yeah. Good point. Okay, so anyway, right? So this is somehow, yeah, right. So this is achievable. And as I said, right, there's this issue with the K that we cannot take the regularization here. And it's this threshold for the capacity, the threshold theorem for the capacity, where the overall threshold that we have. So the statement that we want to make is that for every quantum channel T and any delta, then we can achieve this rate, right, using coding schemes affected by this Pauli IID noise, as long as the strength of the circuit level noise is below this threshold. But this will now depend on the channel T. So this is somehow the drawback of this technical issue, that we don't get a threshold that is uniform over the channels, but it depends on the channel T. Yeah. So I think yeah. Okay. Does this make sense? So yeah, it's, again, right? So yeah. Yeah, I suppose that the rate R is, yeah, that is larger than this is achievable. Yeah, okay. Not
Makes
any.
sense. Yes.
Mm-hmm.
So bringing it back to the real world.
Yeah. So it means somehow that if you have some circuit level noise below this this quantity, then you can get arbitrarily close somehow to the capacity, right? So you have to modify your scheme, but some of the quantum capacity is fault tolerant in this sense somehow.
And also, this is such that if you have a specific construction and a specific architecture, then this variable, all of these variables, the threshold is, you can calculate this explicitly.
This is maybe a very strong statement. So I think yeah. Yeah, so for example, right, it's not even known how to compute the capacity, right? So I suppose I can the threshold. This is something that I can in principle compute, right, by putting in different case here. But I mean, there are these, for example, there are classes of channels where this quantity will be 0 up to some fixed level k, and then jump to something positive afterwards. So this some of this is not very behaved. So I'm not sure that I can actually yeah, compute it in a very rigorous sense. Of course I can, yeah. It's as explicit as I wrote here, but there are some issues maybe.
Okay. Have you
but
tried?
Also, I mean, these schemes they're not non-constructive. Yeah.
Yeah.
Sorry.
Just a question. So have you tried like calculate this circuit level as your papers, these kind of things, using the quantum depolarizing channel, these kind of things, to get some like expression of this threshold?
Say again. Sorry.
Yeah. Have you tried to calculate this threshold based on the, for example, the quantum depolarization channel?
So we have.
Because we are doing a lot of coding approach actually, trying to, it's like what we are doing in IB and stuff, and we actually quite wondering what kind of this threshold should be, because from what our understanding now, you are including this kind of circuit level noise, which is actually very also active for IBM people they are looking at. So when you see the error probability curve, they actually also wondering what's the threshold for this kind of circular label.
Yeah, but I think it's very difficult. I mean, so I mean, there's also always this gap what you can prove and what would actually be true, right?
Yeah.
And so I'm not sure that it's so helpful in this case to compute it. So or to try to compute it, because I mean, presumably what we can prove will be orders of magnitude below what might be true, right? So so then what? Yeah, is it so helpful? I don't know.
Yes, I see.
Yeah. So I mean, so what we have done is, so there are these asymptotically good code constructions by Kelderbank and Shaw. And for this, you can get somehow a more explicit way of doing this. So this we have done.
Yeah, so but for example, like a service code you just mentioned in your talk, right? And for easier case, the simpler case, which referring to the depolarizing channel, they know the threshold is 0.19 around.
Yeah.
And that can be theoretically computed by this kind of result actually. So I'm just wondering whether this is possible to generalize to circuit level case. If we do, then we have more like a principal guideline about the threshold for circuit level.
But I feel the circuit, I mean, the fault tolerance threshold is much more difficult to compute than even than the capacity threshold, right? So you have to.
Yeah, but how for example, say in your theory, the threshold theory, is it possible to calculate your Q delta T given the channel?
Yeah, I mean, like I wouldn't even know how to compute the Q in this theorem, right?
Okay.
So, here.
I see. I see.
I mean, I know the theorem that comes out of the proof here, but it's very bad, right? So it's not not the best you can do. I mean, to prove a theorem like this is very complicated. And yeah, I would love to know more, would have a more analytic way of understanding this, but I think it's
I see, I see. So even the Q here is also like theoretical, like based on some assumptions or something like that.
yeah, like I mean, fix the simplest noise model, like this Poisson noise model. Then I think for this yeah, I'm not sure that the best threshold is known for even for this concatenated scene code.
Oh, okay, I see.
I'm not sure, but I would not be. I mean, I think it's. I think there are estimates, but it's not
the exact values. But okay.
Yeah.
So we are running a little over time.
Yeah, thank you.
Okay, so let me just yeah, thank you for the attention.
Oh, okay, we were at the last slide.
Yeah,
Well,
yeah.
thank you. So unless there are some quick questions from the people remaining, I will thank you again, Alexander, for this very nice presentation.